Hello, and we are back for part 3. So we are still in MAC2311. We are going over section 3.1. We have talked about the constant functions. We are still talking about power functions. In the last video, we looked at how to find the power rule. We found the power rule taking the derivative of 3 different functions to different powers, where p was equal to 1, 2, and 3. So this video is going to focus on proving the power rule, proving how we take the derivative of power functions, and how we can follow the same steps every single time, no matter what our power equation or power function looks like. So we're going to skip through the slides that we have already looked at, and we find ourselves looking at the binomial theorem. So I'm going to pull myself up a little bit. All right, so the power function uses the binomial theorem in its proof. And the binomial theorem is quite daunting. I'm not a fan of it, but it is necessary to prove our power rule. So the binomial theorem states that for every quantity x plus h to the power of p, we can expand this function to x to the power of p plus px to the power of p minus 1 multiplied by h, plus p multiplied by quantity p minus 1 over 2 multiplied by x to the p minus 2 multiplied by h squared, plus a whole bunch of other terms that have h to the power of some number, some quantity, and our last term is h to the power of p. So these all have an h in it. All of this section has the variable h in it. And it's okay to write it as plus ... plus h to the power of p, because we will eventually be plugging in h into our equations, and when we plug in h as a limit, usually is 0. So if you have any further questions about the binomial theorem, please ask the professor. I've tried my best to understand it, but I'm still a student just like all of y'all, and I will admit that I do not fully understand the impact and the importance of the binomial theorem quite yet. And that's okay, because this is my first calc class in college, and I feel like we're all in the same boat, being a little confused by the binomial theorem. So we'll hopefully be able to ask the professor a little bit more about this. So we reach our proof, and this can be a little hard to read. I was having quite a bit of computer trouble making this presentation, but hopefully you can read it, and I will read it out loud as we go through the steps of our proof. So if f of x is equal to x to the power of p, then f prime is equal to the limit as h approaches 0 of quantity x plus h to the power of p minus x to the p over h. So this is the definition of the derivative. And to expand this x plus h to the p minus x to the p, or just this, we are just expanding x plus h to the p, because in this last slide, that is all this is. This is the first term in our numerator of the definition of the derivative. So let's get into it. So when we expand this, we find that the limit as h approaches 0 of x to the power of p plus p times x to the power of p minus 1 over multiplied by h plus p times p minus 1 over 2 times x to the p minus 2 times h to the power of 2, plus a whole bunch of other terms that have the variable h in it. We do not have to write it. You can if you want, but we don't really need to. We don't worry about all of that. We're focused on the patterns that we find and proving how to differentiate a power function such as this, minus x to the power of p over h. So this last term is just this minus x to the power of p. That's all this is. From here to here is our binomial theorem, expanding our first term of our numerator. And we can simplify this by canceling our first and our last term, that x to the p and the subtraction of x to the p, leaving us with the limit as h approaches 0 of p times x to the power of p minus 1 times h plus p times p minus 1 over 2 times x to the p minus 2 times h squared, plus a whole bunch of other terms with h in it, plus h to the power of p. And just like in all of our examples in the previous video, we are pulling out the h. We're pulling out one h out of all of our terms in our numerator so that we can cancel it with our denominator. So we have the limit as h approaches 0 of h multiplied by the quantity of px to the power of p minus 1 plus p times p minus 1 over 2 times x to the p minus 2 times h plus a whole bunch of other variables or terms with the variable h in it plus h to the p. And when we cancel that h in the numerator and the denominator, we are left with just the binomial theorem here without its one h variable. So we have the limit as h approaches 0 of px to the power of p minus 1 plus p times p minus 1 over 2 times x to the p minus 2 times h plus a whole bunch of other terms with h in it plus h to the power of p. And when we substitute in that 0 for h, all of these terms, this term here, this big nasty one, becomes 0. It's multiplied by 0, it becomes 0. All of this plus blah, 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 blah terms are multiplied by 0 because h is being substituted in with 0. And this is also substituted in as 0, leaving us with the limit as h approaches 0, of p times x to the power of p minus 1. And this is still our power rule. It's p times x to the power of p minus 1. So I will give you a minute to write all that down. I know I talked pretty fast, so let's just look at this. If you're having trouble reading this, I can write it on a piece of paper and take a picture of it and send it to you or post it somewhere after this video. I can't get it any clearer on my screen either. So yeah, if you have any questions about how we proved the power rule, feel free to ask after the video, and I will do my best to explain it. Once again, we are highly reliant on the binomial theorem, and if you don't fully understand the importance of the binomial theorem or where we got that from, please ask. I don't fully know where the binomial theorem came from either, but we're all in this together. We're all learning together how to differentiate power functions. So, all right. And if you need more time, you can always go back and watch these videos later. So there are some special cases for power functions. These special cases are when p is no longer a positive integer exponent. Yikes. So sometimes p can be negative. We can have negative exponents, and we can also have fractional exponents. Fractional exponents usually look like a square root. When something like x is raised to the power of 1/2, that is the square root of x. We learned that in like our algebra classes, our pre-calc class, but if you're still struggling with fractional exponents or even negative exponents, I highly suggest using like Khan Academy or some other sources to practice that, because they can be tricky to learn, but very easy to identify once you have learned them. So we're going to look at a couple examples of where p is negative and where p is a fraction. So when our power, our exponent p, is negative, we can still use the power rule. So find the derivative of f of x equals x to the p when p is negative. So f of x is equal to x to the power of -1. When we use the power rule, which is f prime of x is equal to px times, or to the power of p minus 1, then we can substitute that in. So f prime of x is equal to -1, which is our p, times x to the power of -1, still our p, minus 1, which is the same as -1 times x to the power of -2, so negative x to the power of 2. I don't know a prettier way to write that. I'm sure there is one, but this is fine. If it's not fine, someone please let me know. But in my previous calc class, we just didn't care. Once we got our answer, we're like, oh, that's fine. But please let me know if that's not okay. Moving on to fractional exponents, find the derivative of f of x is equal to x to the power of p when p is a fraction. So I think I went over this a little bit in the last slide, but when f of x is equal to x to the power of 1/2, and the power rule states that f prime of x is equal to p times x to the power of p minus 1, then we just substitute that in, and we have f prime of x is equal to 1/2 times x to the power of 1/2 minus 1. Our coefficient remains 1/2 multiplied by x, and when you subtract 1 from 1/2, you end up with negative 1/2. So that's 1/2 times x to the power of negative 1/2. Generally, you can make this look like 1/2 times the square root of x, or the negative square root of x, I believe is what it would look like. But it is up to you how far you simplify your solutions. Some of the homeworks might require us to simplify it more, but generally computers are good at understanding what we mean, even if it's not fully simplified. So I believe that is all I have on the power function. I will give you some time to write all of this down and to maybe write some more notes to yourself regarding the special cases. But these cases prove that the power rule is always usable. We can always use the power rule when we have a power function. When we have any function that is f of x is equal to x to the power of some number, we can use the power rule thanks to our proof, thanks to these special cases, thanks to the binomial theorem. So again, so if you have any questions, please feel free to ask after the video. In the next videos, Tahara will be discussing how to take the derivative of polynomials and exponential functions. So we can't wait to learn about those. If you need any help, I am not an expert. I definitely suggest asking the professor and using external resources. Maybe look at the textbook as well, and even check out Khan Academy. There are some helpful hints and tips in there, especially when dealing with different types of exponents. It's a simple algebraic skill that a lot of us looked over in our previous math classes that I find very important. So yeah, I hope you learned something from this. I hope you found this helpful and that I did an okay job here. And I will see you guys later.